Have you ever stopped to think how your phone just knows how to pull up a photo or a contact in a split second? I mean, it really feels like magic, right? Well, underneath all that, there's this incredibly elegant secret language being spoken between the processor, its brain, and its memory. And today, we're going to crack it wide open.
So, to get our heads around this language, we first have to ask a pretty simple question. What's the deal with your phone's processor? Why is it so picky? Turns out it has some really strict rules about how it's willing to handle your data.
The best way to think about it is this. Your processor is like a brilliant master chef. The chef is unbelievably fast, but they've got one non-negotiable rule. They will only work on ingredients that are placed right there on their personal cutting board. Now, in the world of processors, this cutting board is a set of super fast, easy-to-reach memory spots called registers. And here's the catch, the real kicker. The chef is absolutely 100% forbidden from walking over to the main pantry, which is your phone's main memory, to get ingredients themselves. This is the whole idea behind what's called a load store architecture. All the actual work, the chopping, the mixing, all the math and logic, it can only happen on those registers. So yeah, this creates a bit of a logistical problem, doesn't it? So if the chef can't leave the cutting board, how do we get the ingredients from the pantry? Well, you hire some kitchen staff. And in the processor's world, this staff is made up of two essential instructions, load and store. It's a really simple but powerful division of labor. The load instruction, we call it LDR for short, its whole job is to run to the pantry, which is the memory, grab an ingredient and place it on the cutting board, a register. And on the flip side, you have the store instruction, or STR. It takes the finished dish, the result of the chef's work, from the cutting board and puts it back into the pantry for long-term storage. Okay, but just having a staff isn't enough, right? For a high-end kitchen to run smoothly, that staff needs to be smart. They need to be efficient. They can't just be running around aimlessly. This is where ARM processors get really clever. They give the kitchen staff 3 special techniques or addressing modes to fetch those ingredients with maximum efficiency. So, technique number 1 is called pre-indexed with write back. Now, I want you to look closely at the syntax here. See that tiny exclamation mark at the end? That little symbol is everything. It's a powerful command that basically tells the processor, hey, first, figure out the address I need by taking the base and adding this little offset. Go grab the data, and here's the important part. Once you've got it, update my original base address to this new spot you just calculated.
Let's see how that actually plays out. Let's say our base register, R1, is pointing to memory address 9000. This instruction first calculates the target, 9000 plus an offset of 4, which gives us 9404. Then it loads whatever data is at that location into our destination register, R0. And finally, because of that exclamation mark, the write back, it updates R1 itself. So R1 is now permanently pointing to 9404. It's already ready for the next move. So the big idea here is this. It's like you're going down a shopping list, you grab the first item, and in one single fluid motion, you cross it off and slide your finger down to the next one on the list. Super efficient. All right, let's move on to our second technique, which builds right on top of the first. This one is pre-indexed without write back. Now take a look. Notice what's missing. That's right, the exclamation mark is gone. This tiny change in the code completely changes what happens. It means we're still going to calculate a new address with an offset, but, and this is key, we are not going to permanently update our base register. So if our register R1 starts at 9000 again, we calculate that temporary address of 9004, and we load the data from there into R0. But once that's all done, R1 is still pointing right back at 9000. We never lost our original spot. This is absolutely perfect for when you just need to quickly peek at some data that's nearby, relative to your current position, but you don't want to actually move there. You're just looking at something down the aisle, but your shopping cart hasn't moved an inch. And that brings us to our third and final technique, post-indexed addressing. Now you got to pay close attention to the syntax here, because the offset is now outside the square brackets. This little change signals a total flip in the timing. It's basically saying, go get the data from the location I'm currently pointing at right now, and only after you've safely got it, then go ahead and update my pointer with the offset. So let's say R1 is at 9000. This instruction goes directly to 9000 first and loads that data into R0. Once that data is secure, then and only then does it update R1 by adding the offset, moving it to 9004. It's access first, update second. A total reversal. This is hands down the most intuitive and common way to go through a list of items. You grab the thing you're working on right now, and as soon as you have it, you automatically get ready for the next one. This is the bread and butter of stepping through an array of data efficiently.
So let's just put it all together. Think of this table as your cheat sheet. For the two pre-indexed modes, the address is always calculated before you access the memory. The only difference is whether you update the base register. With write back, that's a yes. Without, it's a no. Simple. And post-index just flips the whole script. You update after the access, which makes it absolutely perfect for just marching down a list.
Okay, so that's all the theory. But where does the rubber actually meet the road? I mean, what does this look like in the real world? Let's take a look at a classic scenario, just walking through an array of data, like a list of numbers or maybe the contacts in your phone. So let's imagine our register R1 is a pointer, and it's starting at the very first item in our array. We use our trusty post-indexed instruction. This tells the processor, hey, go to the address in R1, load that first element into the R0 register so we can do something with it, and then update R1 to get ready for the next one.
And here's where the magic really happens. Because we used post-indexing after that very first load, R1 was automatically and instantly updated to point to the second element in the array. So when we run the next load instruction, it's already in the perfect position to just grab the next piece of data. No extra steps, no wasted time. It's just incredibly efficient.
All right, you've seen the theory, you've seen it in practice. Now it's time to put your newfound knowledge to the test and really see the power of these modes when they work together. Let's solve one last puzzle. Okay, here's the setup for our pop quiz. Register R1 starts out at memory address 9000. And we know that way over at address 9404, there's a piece of data stored. The question is, what are the final values going to be in registers R0, R2, R3, and R1 after we run this exact sequence of 3 different load instructions? All right, let's break it down step by step. First up, the pre-indexed with write back. It calculates 9000 plus 4, which is 9004. It grabs the data from there and puts it in R0, and then, click, it updates R1 to 9004. Next, we have a simple pre-index load with no write-back. It just looks at the new address in R1, which is 9004, and copies that same data into R2. R1 stays put. And finally, the post-indexed instruction. It loads from R1's current address, which is still 9004, into R3, and only then does it add 4, moving R1 to its final destination of 9008. So after all that, why does this super low-level detail actually matter? Well, because this is the secret language of speed. That instant, buttery smooth scroll through your photos, that's array processing using these exact efficient instructions. The ability for an app to manage its memory and not crash, that's stack operations. This isn't just theory. It's the fundamental reason the devices in your pocket, on your wrist, and even in your car feel so fast and responsive. This elegant little set of rules is just one tiny layer of the incredible hidden machinery that powers our world. It really makes you wonder, doesn't it? What other invisible, elegant rules are out there, quietly making our entire digital lives possible?